Hi everyone, welcome back engineers. Today I am going to discuss the single cycle path in this video. Now you might think you already know this topic because it is the absolute basic rule of timing analysis. But let me warn you, this is where interviewers love to hide their trickiest trap questions. To make sure you are completely prepared, at the end of the video, I will discuss some real tricky interview questions that top semiconductor companies do ask. So without any further delay, let's get started. So what exactly is a single cycle path? Think of it as the default way data travel inside a chip. Now you have a starting point, that is the launch flip-flop. You have an ending point, that is the capture flip-flop. Now here comes a golden rule. So what does that golden rule says? It says that when the clock ticks, the data leaves the launch flop or the launch register and it then travels to the logic gates. That means the combinational logic circuit and wires, and it reaches, that means it arrives at the capture register. So if this is n age, it should capture at n plus 1 age. That means the next clock age. Okay, so if it is n clock age, this is the n plus 1 clock age. That means your circuit has exactly one clock cycle to move its data from start to finish. So if an interviewer asks you for a baseline timing path, this is exactly what you are going to describe. Now here is something interviewer love to ask. What happens if you don't write any timing constraints for a path? The answer is very simple, right? The tool, like the EDA tool, whatever EDA tool we use, the timing tools like Synopsys Prime Time or Cadence Tempest automatically apply a default rule called single cycle assumption. So whenever we are not giving any timing constraints, it should just it just should the tool should treat it as a single cycle. Okay. So how these STA tools do behave? So every STA tool will have a common model or a common algorithm. So how those model works? The model works in such a way that the moment the software sees a path without any special instructions or without any special constraints mentioned, it just locks its internal matrix. It sets the launch age to exactly 0 nanosecond and it automatically demands that the setup check must happen at the very next clock age. Now notice how both launch age and this hold capture check are both pinned to the same exact same 0 nanosecond mark. Because they are locked together, changing your clock speed will never move them apart. That means this is the ultimate proof you can show an interviewer to explain why hold checks completely ignore your clock frequency. So we all know, right? Hold is a independent of clock frequency, right? So this is the exact reason. I'll explain it using an waveform. Now let's look into this clean diagram to see exactly how these STA tools think. Okay. Now look at this top line. This is the launch clock. This is the capture clock. Now if you look into this launch clock, what it is saying, the tool locks at the starting point. That means that this is the launch age. Okay, this is the launch age to exactly 0 nanosecond. This is the launch age. So this entirely is the timing window. Let's consider like that. So this is the launch age. So that means this is the exact moment from where the data is sent out. Okay. Now look at the bottom line. So this is the place where the tool will consider two checks actually. So when we are planning to capture the data, there are basically done two checks. We all know that. One is setup check, another is hold check. Now the setup check. For setup check, how we do that? Now follow this long arrow you all can see, right? So what does it mean? What it is expecting? The tool expects the tool expects that your data to travel across the chip and arrive safely before the next clock age, before the next active clock age rises at age 1. So this is the age 1. So basically the setup will be checked at this point, exactly here before the active clock age, where my mouse I'm moving here, exactly on this point the setup check should be done. That means the data should get captured before that. Okay. Next is hold. For hold, what you are seeing, this is a short vertical arrow at 0 nanosecond in the capture clock. That means it makes sure that your data does not move too fast and override the previous data cycle. So it should check only at the same edge as the launch clock. Okay, that's why we say that hold is independent of clock frequency. It doesn't depend on clock period because it is checked on the same edge. It is checked on the same edge, exactly same edge, exactly same edge as the launch edge. Okay, now uh, now what we have to see, this is the setup check. We all know this is a max delay. We say setup checks are done at the max delay. So that is the worst case scenario. So what we know about setup, what is setup time? So setup time is basically a very minimum time before the next active clock edge where the data must be stable to get captured, right? Now what it is saying that we have a data arrival time, we have a data required time, and then we have to calculate the slack, setup slack. That means based on setup slack, if we are getting positive slack, we will see like there is no setup violation. If it is negative slack, that means there is a violation. So that's how we do check. So this is just the formula given. Okay, that's how we do the calculation. So arrival time means the actual time. So how we will calculate the data arrival time? We do launch clock delay plus clock to queue delay plus logic delay, that means the combinational delay, plus the routing delay, that means the wire delay. Okay, so we'll do the routing. So routing will also have a delay. What should be the data required time? The data required time should be clock period. Now let's consider here it is single clock. So single clock period plus capture clock delay minus setup time. That means that minimum time before the clock is that minus setup time minus uncertainty. So there will be some, due to some timing variations or some some jitter, we will have some uncertainty. So now we got both arrival time and data required time. Now how the equation for setup works? Setup slack is equals to data required time minus data arrival time. That means data required time should be always more than the data arrival time. That means the data must reach before the required time. That's the only thing. Now I'll explain it. How does it work? So let's use this waveform to see how the setup check works in real life. So look at this top block. So here we have a clock. Okay. So if we see the data starts its journey. So if you see the data starts its journey at the clock edge n. This is the edge n. Okay. And must safely, it should reach much safely before the n plus 1 edge. Okay. This is the n plus 1 edge and it safely must reach before n plus 1 edge. Now the distance between n and n plus 1, this is called as clock period, one clock period. This is entire one clock period. Okay. From age n to n plus 1, this is entirely one clock period or our clock period, you can say. Here we are considering single cycle, that's why it's one clock period. Okay. Now see this next launch flop or the launch register, you can say. Both are fine. So launch flop, if you see launch clock or launch flop or launch queue, launch flop, launch register queue. So if you see it, the moment the clock rises, the data takes a tiny fraction of time. That means it basically like it is taking a particular time to exit the flop, right? So that time we call as clock to queue delay or TCLK to queue, we write like that. Okay. Now look at the third one. So this third is the capture register D. Okay, we just named it like that. DQ like that. Okay. Now if you see here, what does it shows? So if you see the data is traveling through a long path of logic gates and wires. Okay. The data is traveling through a long path of register and wires. And logic gates and wires. So now the total time from 0 nanosecond to the end of this time, this end of this portion, this is what we say 0 to this portion we call as data arrival time. So this small dotted line says data arrival time. So the data must reach before this time, must reach here, okay, by this time, or the data must reach before this time, okay, before the required time. So last is the age n plus 1, that is the capture age. So before the required time, the data must reach. Okay, so till between this time we will calculate the setup slack. So if the slack is coming in between this, that means it's a positive slack. Okay, that means if data is reaching before required time, that means it is called as positive slack. That means there is no violation in the slack in the setup. To keep this chip safe, the data must be stable before a strict deadline. So our strict deadline is this required time. Okay, now if you see this green gap, so this green gap is basically the act. What is the difference? There is a difference between the actual arrival time and the deadline, that is the data required time. So this is where we check the setup slack. So as long as the data settles here, we will say like setup check passes. So there is no violation. If it goes beyond this data required time, that means there is a violation. Okay, now just for interview purpose, you must be careful with the concept that if the gray block grows too long, what I'm saying, right? If this gray block, if it grows too long, so too many logic, like it can be because of bad routing or too many logic gates are sitting. So it will push the deadline, right? So that will create a setup violation. To fix it, either you have to speed up the data or slow down the clock. So either of the way you can do. We will discuss that later, how to fix the setup. So next, just look for the hold check. So what we know, that the hold check is done. How it will be done? Exactly. It will see, it is preventing newly launched data from moving too fast, and it is destroying the old data before the register can safely read it. That means we don't want the data to get overwritten. Okay, so how the data arrival time is calculated? Here for hold, the data arrival time is calculated like launch clock delay plus clock to queue delay plus minimum logic delay, that is whatever the combinational delay we have, minimum routing delay. Okay, and the data required time is capture clock delay plus hold time plus uncertainty. Okay, so the hold slack is just the opposite to setup slack. So hold slack is equals to data arrival time minus data required time. That means the data arrival should be more than the data required time. Okay. So we'll explain that using a waveform here. So as we know, hold checkup means it's a minimum delay constraint we are doing. Okay. So let's look at how the hold check visualizes on a waveform. Okay. So look at this top block. So at the top block, the clock we are seeing, the data journey starts at age n. Okay, which is our launch age at 0 nanosecond. Now notice that the next clock age is where uh, the next clock age is nowhere to be found. So there is no next clock age, right? We are just seeing that the starting age is age n, but there is no next clock age because the whole checks do not care about clock cycles or frequency. That's how we can say that the hold is independent of clock frequency or the clock period. Okay, now look at this middle launch register queue. So the data exits our first flip-flop after a short delay marked by this we are seeing this, right? A small gap in this. So there is after a short delay. So this is like marked by a clock to queue delay. Okay. So this is where we are calculating clock to queue delay. So here it's like the data is exiting from the first flip-flop. Okay. And now look at this bottom register. This is the capture register. Now in this, what it is happening, this is the first path. Okay, this is the fast path. Okay, so in the first path, what it is happening, so the data changes quickly at 4 nanosecond. See, the data is changing at 4 nanosecond. Okay, it is changing, right? Here there is a change from 0 to 4. At 4 it is changing. So this is basically the arrival time. So if you see, this is the arrival time and this red dotted line is the required time. So as we told, for hold, arrival time should be more than the required time, right? So to pass timing check, this new data must not arrive too quickly. The destination register needs a tiny bit of time to save the old data safely. So that requirement is marked by the dashed this one. So it should come in between. So whole slack will be positive, whole slack will be negative only if it is here. So basically negative slack benefits hold like that. Okay, so data must be here for some time so that the data gets some time to get captured. Okay. So that requirement is marked here, and this is called, so this is the data required time and this is the data arrival time. So the safe gap here between arrival and the required time is giving us the whole slack, because the data arrived comfortably after the deadline, and our whole check is perfectly safe, and we can say that the slack is positive. The slack should be positive enough. Okay, like the value should be positive enough. Okay, but in the calculation wise, we will see the data arrival time is more than the data required time. Okay, now let us talk about a huge balancing act in chip design. So that is called clock skew. So this is just the time different between the clock arriving at the launch register versus the capture register. So a common question interviewers do ask usually that does clock skew ever favor hold? Now the answer depends entirely on the direction of the skew. So look at the first column. If you see the first column, I'll give you an example after some time. Uh, so if you see, when we have a positive skew, the capture clock arrives late. So that acts as a frame to set up because it pushes the deadline out. Okay, so it will give our slow data more time, like it will giving our slow data more time to travel. But it is a massive enemy to hold. Why? Because the capture register stays open longer. Fast data can easily crash onto it and ruin our chip, right? Now, if we have a negative skew, like shown on the second column, if you see, if we have a negative skew, so what it is doing, the capture clock arrives early. The capture clock is arriving early. So this closes the register quickly, which is fantastic for protecting our hold margins. But the trade-off is that it steals time away from your setup check. So basically, it is not benefiting setup. Okay, so we have to remember this, that simple rule for our interview. What helps setup will always hurt hold, and what helps hold will always hurt setup. Okay, I'll give a very simple example to remember the, or to understand the concept of this setup and hold. Okay, how setup failure happens and how hold failure happen. So in a real chip, the path breaks in between data, like paths will get break because data moves at the wrong speed, right? It should not go too fast, it should not go too slow, right? Now think of it like a traffic jam versus a drag race. Okay, now let's consider this a traffic jam. Okay, now look at the left side of the screen, and if you see, this is our setup failure. So here the data path is caught in traffic jam. There are too many logic gates, or the wire is too long. So if you see, there are too many logic gates, or the wire is too long. So the data moves so slowly that it misses the train, the next clock edge. Okay. Okay. So now to fix this traffic jam, what we can do? We must upgrade the engine. Okay. So we must change the logic gates to physically bigger. That means the ultra fast cells that can push the signal through quickly. Okay. Now bigger engine can, obviously, if we are upgrading the engine, that has the capacity to make it faster, right? Or drive it faster. Same way, now look at this right side where hold is failing. Now this path has no logic gates, nothing. The data accelerates so fast that it crashes into the previous data cycle and it destroys it. To fix this drag racer, you need to speed bump. Okay, you need to use some speed bumps. So as a physical design engineer, what you are going to do, you are going to place some small delay buffers onto the wire. So this forces the data to slow down just enough to let the clock edge click safety shut. Okay, I'll explain that in terms of setup and hold. So we all know exactly how the setup violation, why the setup violations do happen. So when the data is too slow, that time we see the setup violation is happening. That means the data is arriving very data is too slow, means the data arrives very late than the data is expected to reach. Okay, so because the data must arrive before the required time, right, for setup. The data must be arriving before the required time. So if it is too slow, it will reach after the required time, right? So the data is too slow. So why it generally happens? Might be because it has too many logic depths, or like 20 plus gates, or multiple number of gates in a row. That can be a reason. Or might be too much long routing has happened, like a lot of physical distance is there, like with a lot of parasitic RC delay is there. That can be another reason. Then again, the worst case scenario can happen, that is the worst case corners are there, high operating temperature, that can affect, or the lower supply voltage that can affect. So these are the factors that will generally affect setup. Okay, so how to fix them up? To fix them, we need some up driver cells, because the up driver cells are characterized to drive higher output current. So that will, like, all those it will help the transistor to deliver higher output current and charge the wire capacitance faster. Okay, another option is we can go with swapping the VT cells. So if we are going with lower VT cells, it is helping us, like lower threshold voltage will help us to turn on much faster through, though they are little leaky, but we have to balance on that. Like if we are using ULVT, we need to come to probably LVT. Like if we are using HVT, we may come to SVT, or we may come down to LVT. So it depends. You have to balance that. Another option is structural pipelining. So we can ask the front end designers to modify the RTL code to insert some intermediate registers and cut a long path, and we can add some single cycle segments in between them. So that can be possible. Now for hold, what is the thing? Hold means the data is too fast. So what can make it fast? The registers, like it can happen that the shortware paths are there. That means a zero, very less space is there, near zero routing delay is there. That can happen. Or probably there are like no logic gates are there, shift registers or direct buses are there, so it is just removing any propagation delay. So that can be a reason. Or the best case scenario, what we call it as first process, first corner. Okay, so the first corner can also affect, because like especially at lower operating temperature, or probably with supply voltage is not like supply voltage is too high, so that can also speed up the things. Okay, so what we can do to fix this hold, we have to add some delay buffers. Now what we can do, we can drop some non-inverting delay buffer cells straight into the data wire to act as a like a speed bump to stop it, okay, or to slow down the signal. Okay, or we can make the routing layer little longer. So we can make little longer wide routing layer, or we can use some slower metal tracks. Okay, so those are the main way of fixing hold violation. Now this is just an example, I'm showing it out here. So this is setup optimization, how do we do, and this is hold optimization, how do we do. So as I told, setup optimization, if we have a long logic chain, let's say a lot of logic gates in a row, that time we can compress it and resize it. So we can take little bigger, upsize the buffers, or we can upsize the cells, and then we can use less number of logic gates in a row. So that will help to fix setup. For hold, if we have a very big ultra fast wire length, like routing without any logic gates, there we can insert some delay buffers just to slow it down. Okay, now let's discuss on how uh like after this single cycle, I know everybody has already have a good concept on single cycle timing analysis, but there are certain frequently asked interview questions that I'm going to answer today. Okay, so the first question says, what happens if you don't write any timing constraint for a path? It's a very commonly asked question. Usually people will get nervous with the question, but it's a very easy thing. Everybody knows that, right? So by default, we know the STA tool treats the path as a standard single cycle path. So it automatically assumes data must launch on one clock edge and capture on the very next consecutive clock edge. That means it is taking exactly one clock period if we are not defining any timing constraints for a path. If we are defining any timing constraints means okay, for that we can consider. But if we are not defining means by default the model will take it as a by default single cycle path. Okay. Now the next question is, if a design contains multi-cycle paths but you provide no SDC exception, what will the STA tool do and what is the impact on physical design? Well, obviously to answer that, the tool the tool defaults to a single cycle clock, right? Now, severely over constraining the path in physical design, the tool will waste area and power by aggressively sizing of the buffers, right? And also it can use up high leakage cells to meet an impossible one cycle deadline. So we should not do that. That is one of the recommendation. Okay, so that's why we must provide an SDC exception. We must provide an SDC file where we are defining properly all the constraints defined in it. Otherwise, it will affect some or the other way because the tool knows it as a, if we are not defining any exceptions or any constraints onto it, the tool will by default take it as a single cycle. So it can do anything. It can, because it is now over constraining, right? So like it can do anything. It can waste your area, it can waste your power, like by upsizing the buffers also, and also by that high leakage cells can be added up. So that's one of the reason. Okay, now another commonly asked question is, walk me through the mathematical components of a setup check. How does clock uncertainty affect it? Well, we already knows that clock uncertainty acts as a safety margin for jitter, right? It's a part of jitter. So it subtracts directly from the required time. As I showed it in the formula, it directly subtracts directly from the required time. And it is narrowing the timing window and reducing your setup slack. That's how you can explain. You can just write out the formula and you can just explain through it. Okay. I'll explain this particular question on a separate video. I know it's not so easy to explain. I'll make it in a separate video how the uncertainty is affecting both setup and hold. Okay. Just as a rough, I'm just telling it that it just basically reduces your setup slack because it subtracts from the required time. Okay, that's it. Now, how does changing the clock frequency affect your hold slack? Well, changing the clock frequency does not affect the hold slack. We have seen that in today's video, right? Hold time depends entirely on data path, not on the clock path. Always remember that hold time depends entirely on data path delay and clock skew between the launch and the capture flops, not on the clock period or frequency. That we must remember. Next is, how does positive clock skew affect setup and hold margins, and how can you exploit this in physical design? Well, positive clock skew delays the arrival of the clock at the capture flop, so which improves the setup margin by giving data more time to arrive. But it is worsening the hold margin by requiring data to remain stable longer. Obviously, what we said that clock skew will sometimes benefit setup, but it won't benefit hold. Vice versa, it will happen. So in physical design, as an engineer, so engineers exploit this through useful skew. As an engineer, how we can do, we usually use some useful skew here. So here our idiot tools will intentionally delay the capture clock of critical paths to fix setup violations. Okay, so intentionally we are using this useful skew. Okay, so this technique basically borrows the timing slack from non-critical paths with margin to spare, allowing the entire chip to run at a higher frequency without changing the logic gates. That's it. Now, next question is, when you run timing analysis, you will inevitably find broken paths. How do you fix them as a physical design engineer? So, as I have already discussed on here, so how to fix them, you can just go through it. Okay. Now, imagine you have an optimized design ready for tape out, but you discover a setup violation on path A. and a hold violation on path B. Which one do you prioritize fixing first, and what is your overall strategy? This is a very, very common tricky question that interviewers do love to ask. I think I have faced this question multiple times in my career. So, as an engineer, how can I reply to this? I will say that I will always prioritize fixing the hold violation first. Why? Now, here comes the answer. A setup violation can be worked around post silicon by lowering the chip's external operating frequency to expand the clock period. We all know that. However, however, the hold violation creates a fatal race condition, right? That cannot be fixed by changing the clock speed because it is independent of clock frequency. So it renders the silicon completely non-functional. So we should not leave hold violation till the end. We must prioritize hold violation. So my strategy would be to use automated ECU routing steps to safely insert delay buffers on the hold failing data path, ensuring that the added delay cells does not accidentally create a new setup violation on adjacent timing corners. So we must keep our eye, we must balance it, we must check things properly so that whatever fixation we are doing for hold, it should not again affect the setup. So we must make a balance out of it. We should not add too much delay buffers also. Okay. The last question is, can a path have negative setup slack and a positive hold slack? Well, a path can have both negative setup slack and a positive hold slack because setup and hold constraints evaluate completely opposite boundaries of data path delay. Setup analysis means it takes the maximum delay limit. Okay, so there is a maximum delay limit we will have. So setup analysis will test that to ensure that is a, we say, the worst case scenario. So it will basically test that to ensure that the data moves fast enough to arrive before the capturing clock edge. That means a negative setup slack indicates that data path is too slow. Now on the other hand, hold analysis tests the minimum delay limit. Why? To ensure that the data moves slowly enough that it does not prematurely override the destination register. So a positive hold slack indicates the path is safely delayed. Because a slow and a complex logic path inherently takes a long time to propagate, generally its sluggishness naturally protects it from failing hold times, while simultaneously it will cause to fail setup times. So again, we need to balance things. We need to analyze things properly. So well, that's all I had to present today. I had to explain it to you guys. I had to share it with you guys. Thanks for watching. I appreciate your time and attention. If this really helped you to clear up the concept, please hit like button. And if you haven't yet subscribed to my channel, please do subscribe it. And also keep tuning on it to keep sharpening your technical skills. We'll meet you on the next video. Till then, keep learning. Thank you.